dear students, let's start Standard 11, Chapter 6, System of Particles and Rotational Motion. See, we discussed about the laws of motion, but when we discussed the laws of motion at that time, we considered an object as a particle, point-like object. But in practice, when we deal with any object, it is not a particle, but it is made by large number of particles. It implies that each and every object have large number of constituent particles. So how we can explain the motion of a system of particles? That also we have to understand. And how we can apply the laws of motion which we studied previously to the motion of a system of particles. Now here, first we will discuss a rigid body, and then after we will discuss how many types of motions are possible for a body. And then after, in this particular chapter, we will concentrate our mind on one new type of motion, that is the rotational motion. We already discussed about the linear or translational motion as well as circular motion also. Now we will discuss rotational motion. So here first of all we have to understand the concept of rigid body, right? Here we will consider a system of particles as a rigid body. Rigid body means what? Rigid body is a body which have perfect and definite unchanging shape. For a rigid body, the distance between different pairs of particles, the pairs will not change, the distance between the pairs will not change. In other words, we can say the rigid body means the body for which the relative positions of the constituent particles never changes. So in other words, we can say rigid body can't be deformed. Solid body can be deformed. Suppose we consider any solid body and we apply some external force on it. Then by increasing the force on it, the solid body can be deformed. But rigid body, as per its definition, we can understand the rigid body can't be deformed, because here we say this thing, the relative positions between constituent particles never changes. Now, when we say rigid body can't be deformed, but a solid body can be deformed. So this is one type of idealization. Actually, in nature, there is no rigid body. But in practice, we consider solid body itself as rigid body when the force applied on it is not deforming the body. So, when we take any solid body, some force is acting on it, under the effect of that force, suppose body execute some type of motion. But during that, if any type of deformation in the body is not taking place, then simply we can consider the body as a rigid body. Clear to all of you? So here we can consider solid body as a rigid body when body is not deforming under the influence of any forces. Otherwise, there is no such real body which can't be deformed under the effect of external force. So, rigid body, that is one type of idealization. Keep this thing in your mind. Clear? Now, next topic, that is what kind of motion can a rigid body have? Rigid body can execute different types of motion. First, we can think about a pure translational motion. Now, in pure translational motion, if we think about the example of a motion of block sliding on an inclined plane. So here, in pure translational motion, the velocity of each and every constituent particle of the body, that will be same one. Or in other words, we can say each and every constituent particle will cover same distance in same time interval, right? So this type of motion, that is a pure translational motion, as shown in the figure. Then rolling motion. In rolling motion, if we think about the cylinder rolling on an inclined plane as shown in the figure, then the center of mass here, say this P1, that execute a translational motion, right? And each and every constituent particle execute rotational motion, right? So, this translational plus rotational, this motion that is known as rolling motion, and this cylinder when moving down to the inclined plane, it execute rolling motion. Then rotational motion, right? In rotational motion, each and every constituent particle of the rigid body perform circular motion, and centers of these circles lies on an imaginary line which is known as rotational axis. That is a geometrical line, and we can say the body is executing rotational motion. See here, if we think about the motion of a fan, then each and every constituent particles of the fan that execute circular motion, and centers of their circular path lies on this geometrical line which is known as rotational axis. So we can say this body is executing rotational motion with respect to this rotational axis, right? So see here, for a rigid body, suppose we have a rigid body having arbitrary shape as shown in the figure. Now here, suppose each and every constituent particle of the body is executing circular motion. If we think about this particle P1, it is executing circular motion. Center of that circular path is C1. For particle P2, it is executing circular motion on the circular path having radius R2, again center of the circular path, that is C2. But if we think about the centers of these all circular paths of the circular motion of constituent particles, then those centers lies on an imaginary axis. That is the rotational axis. That is simple geometrical line. Here in this particular case, as shown in the figure, we can say this particular rigid body is executing rotational motion with respect to z-axis here. So we can say this z-axis, that is the rotational axis of this body. Then after, now next motion, that is precessional motion. See the example of the motion of a spinning top. In precessional motion, the body execute rotational motion. See here, the top execute rotations with respect to this particular rotational axis. And here the rotational axis of the body that swipe a cone with respect to this point of contact of the top with respect to surface, that is O. So with respect to this one, this particular rotational axis swipe a cone. So this type of motion of the body, that is known as precessional motion. Clear to all of you? Now here we discussed the different type of motions which are executed by the rigid body. But now here in this chapter we have to concentrate our mind only on the rotational motion. But before discussing the rotational motion, we have to discuss the concept of center of mass. Why the center of mass of the body? That is very important. That later on we will understand this thing. But first of all, we have to understand what is the center of mass of the body and where it is located. Now, center of mass of the body, that is nothing but a point or the position where entire mass of the body is concentrated. It behaves like that. And always remember this thing, the center of mass of the body, that may be inside the body or outside the body. And when we say this is the point where entire mass of the body is concentrated, means if the body is balanced exactly at this particular point, or in other words we can say, if this point which is known as center of mass of the body is balanced, entire body that will be balanced. Okay? So, what is the center of mass? That now you can understand easily. Now, where it is located. So, here we have to discuss different cases. Suppose we think about the center of mass of a system of two particles. So, if we think about a system of two particles, then that is a linear system. Suppose with respect to the origin of Cartesian coordinate system, one particle having mass m1 that is located at distance x1 on x-axis, and other one is located at a distance x2 having mass m2 on x-axis. So the center of mass of this particular system, right, that is located at a distance x from the origin, which one is calculated by the equation x equal to m1 x1 plus m2 x2 upon m1 plus m2. So center of mass of this system, that is given by this particular point. Clear? So here the entire mass of the body that will be concentrated. Now here x, that is also known as mass weighted average position of x1 and x2. Remember this particular word, mass weighted average position of x1 and x2. Now here, if we consider a special case, suppose both the particles are with same mass, m1 equal to m2 equal to m. Then we can write the equation x equal to mx1 plus mx2 upon m plus m. So, this will be x1 plus x2 by 2. It implies that the center of mass of two particles of equal mass lies at the center of the line joining to these particular two particles. Clear? Now, center of mass of a system of n particles in one dimension. So, we can extend this equation up to n particles. See here, suppose the system of particles, it is one dimensional. So, it is lies on x-axis. So, system of particles have n particles having masses m1, m2, m3 up to mn. And suppose these particles are situated at distances x1, x2, x3 up to xn respectively from the origin of Cartesian coordinate system. Then the center of mass of the system of n particles, that is given by x equal to m1x1 plus m2x2 plus up to mnxn upon m1 plus m2 plus m3 up to mn. So here we can write in short form x equal to sigma mi xi upon sigma mi. Now if we take the summation of the masses of each and every constituent particle, then it will give you the total mass of the system of particles. Clear? So we can write x equal to sigma mi xi upon m. So how we can find the center of mass of one dimensional system? Now it is clear to all of you? Okay. Now next, center of mass of three particles not lying in a straight line in two dimensions. So if we consider a system of three particles and these three particles are not lying in a straight line, then definitely we can say it will be in two dimensions. Means it is a two-dimensional system. Here, if we take the coordinates for the position of these constituent particles of the system as x1, y1, x2, y2, x3, y3 respectively, then if their masses are m1, m2 and m3, we can represent the coordinates of center of mass of this system as xy. So x, that is given by equation m1x1 plus m2x2 plus m3x3 upon m1 plus m2 plus m3, and the y coordinate that we can represent by y equal to m1 y1 plus m2 y2 plus m3 y3 upon m1 plus m2 plus m3. If we consider the three particles here are with same masses, means m1 equal to m2 equal to m3, that is m, then we can write x coordinate as, if we take m common, then into x1 plus x2 plus x3 upon 3m, mm cancel. So x1 plus x2 plus x3 by 3. Similarly, y coordinate that we can give by y equal to y1 plus y2 plus y3 by 3. It implies that in this particular case, the center of mass, that is the centroid of a triangle made by these three constituent particles of a system. Here if we consider a constituent particles are n numbers, right? Means system is made by n number of constituent particles which are not lying on a straight line. Means again we can consider it as two-dimensional system. So in that particular case, simply we have to extend these equations up to n step, or we can write the x coordinate as x equal to sigma mi xi upon capital M, as well as here y equal to sigma mi yi upon capital M. So in this way we can represent the position of the center of mass of a system of n constituent particles and the system which is two-dimensional. Clear? Now next, let's think about the center of mass of a system of n particles in three dimensions. Suppose as shown in this figure, we have a system of n particles in three dimensions. Here, suppose the masses of the constituent particles are m1, m2, m3 up to mn, and their positions with respect to the origin of Cartesian coordinate system are R1, R2, R3 up to Rn respectively. Then the position of the center of mass of the system, suppose here V, consider arbitrarily the center of mass of the system that is at this point represented as C. So its position vector RCM, that is given by vector RCM or vector capital R, that is M1 vector R1 plus M2 vector R2 up to Mn vector Rn upon M1 plus M2 plus M3 up to Mn. So here we can write vector RCM, that is equal to vector capital R equal to M1 vector R1 plus M2 vector R2 up to Mn vector Rn. Or you can write this one like this also. This is equal to sigma Mi Ri upon capital M. Capital M, that is the total mass of the system of particles. Okay. So here we can say capital M, that is the summation of the masses of constituent particles. Clear to all of you? Now next topic, that is center of mass of a irregular shaped body. Suppose the body given to you that is with irregular shape, but mass is continuously distributed in the entire body. Then in this type of case, how one can find the center of mass of the body? Now see, suppose as shown in the figure, we have irregular shaped body and mass is continuously distributed in the body. So here in this particular case, we have to divide this entire body into so many infinitesimal small mass elements. Suppose here this particular body, that is divided into mass elements dm1, dm2, dm3 up to dmn, having position vectors respectively with respect to the origin, that is R1, R2, R3 up to Rn. Then in this particular case, we can write the position vector for the center of mass of the body, that is vector RCM equal to vector capital R, that is dm1 R1 plus dm2 R2 up to dmn Rn upon dm1 plus dm2 plus dm3 up to dmn. Now here the mass distribution, that is continuous one, and due to that this summation that we can represent with integration, because mass elements under consideration are very small, means mass elements tends to 0, right? So we can write the equation RCM, that is equal to vector R, that is equal to integration RdM upon integration dm. Integration dm, that is the summation of mass of each and every element. So it will give you the entire mass of the body. Suppose that is capital M, so you can write the equation integration RdM upon capital M. Now suppose we write this equation in component form, then we can write xcm I caret plus ycm j caret plus zcm k caret equal to 1 upon m integration xi plus yj plus zk dm. Or independently we can write the x, y and z components of the center of mass as xcm equal to 1 upon m integration s dm, ycm that is 1 upon m integration y dm, and ZCM equal to 1 upon m integration ZDM. Clear to all of you? Now next, that is center of mass of a thin rod of uniform density. See the theory which we discussed previously, using that we can find the position of the center of mass for the body which one is with regular shape also, right? So here this one is one simple example. Suppose here, as shown in the figure, we consider a thin rod which one is with mass capital M and length equal to capital L, which one is with uniform cross sectional area and uniform mass density. Now here, that is the linear mass density. It implies that mass per unit length, and here this particular thin rod that is placed on the x-axis in such a way that one end of the rod that is at the origin of the coordinate system. So here with respect to this origin, where will be the center of mass of this rod, that we will calculate here. Now here the symmetry of the rod that is with x-axis, so we can easily understand the position of the center of mass that will be also on the x-axis. Now here we consider infinitesimal small line element having length equal to dx on the rod at a distance x from the origin. Now what will be the mass of this element? So linear mass density, that is mass per unit length, lambda. So that is total mass upon total length. So we can say mass per unit length is lambda. Therefore mass of length dx is how much? So we can write dm, this mass element, that is lambda into dx, where lambda that is m by L into dx. Clear? Now as discussed in the previous theory, the position of the center of mass on x-axis, that will be xcm equal to 1 upon m integration xdm. Now here substitute the value of dm, that is m by L into dx. And here we have to consider this type of elements starting from x equal to 0 to x equal to capital L. So here we have to take the limits of the integration 0 to L. So 1 upon m integration 0 to L x dm, that is m by L dx. M will be cancelled. So we can write now this is equal to 1 upon L integration 0 to L x dx. Integration of x, that is x square by 2. So this is equal to 1 upon L x square by 2, 0 to L, substitute the limit. First upper limit, then minus lower limit. So here 1L will be cancelled. So xcm, that is equal to L by 2. It implies that here we can observe this thing. The center of mass of the thin rod of uniform mass density lies at the center or midpoint of the rod. So here remember this thing, not only for rod. If you find out the position for the center of mass for this type of bodies which are with proper geometrical symmetries, then for all those bodies like circular plate, circular ring, then sphere, then cylinder. So for all these type of objects, the center of mass lies at their geometrical centers. Clear to all of you? Now example 6.1. Find the center of mass of three particles at the vertices of an equilateral triangle. The vertices of an equilateral triangle, the masses of the particles are 100 gram, 150 gram and 200 gram respectively. Each side of the equilateral triangle is 0.5 meter long. So here, suppose as shown in the figure, we consider the equilateral triangle for which three vertices of the triangle O, A and B are as shown in the figure, and 100 gram mass that is placed at origin O, 150 gram mass is placed at point A on x-axis, and 200 gram mass is placed at point B. So here it is given to you the sides of the triangle are 0.5 meter long. So coordinates for the origin O means for the position of the 100 gram particle, that is 0, 0. For A, that is 0.50, and for B, so for B, this angle we consider 60. This is 0.5. So 0.5 cos 60, 0.5 sin 60. So we can write the coordinates for point B, that is 0.25 and 0.25 into root 3. Clear? Now, here the coordinates for the center of mass of this triangle, that we can write as XCM equal to M1x1 plus M2x2 plus M3x3 upon M1 plus M2 plus M. Now substitute the values. M1 that is 100 gram, X1 0 meter, M2 that is 150 gram, X2 0.5 meter, M3 200 gram, X3 0.25 meter upon 100 plus 150 plus 200 gram. So if we solve this one, you will get the result 5 by 18 meter. Now y coordinate for the position of the center of mass, that is y equal to m1y1 plus m2y2 plus m3y3 upon m1 plus m2 plus m3. Again substitute the values. So 100 m1 y1 that is 0 plus m2 150 y2 0 m3 200 y3 that is 0.25 into root 3 upon 100 plus 150 plus 200, that is directly written here 450. Now if you solve this one, you will get the result 1 upon 3 root 3 meter. So we can write the position vector for the center of mass RCM, that is equal to xy, that is 5 by 18 and 1 upon 3 root 3 meter. Clear? Now example 6.2. Find the center of mass of triangular lamina. Now see, suppose as shown in the figure, we have triangular lamina LMN. So here divide this lamina into so many infinitesimal thin narrow strips parallel to the base MN. So by symmetry we can see this thing, the center of mass of each strip, that will be at the midpoint of each strip, right? So here if we join all these midpoints, then we will get the median LP. So center of mass of this lamina, that will lie on this median LP. Now in the same manner, suppose we divide this particular lamina into thin strips parallel to LN. Then if we join the centers, then we will get the median MQ, and similarly third one, that we will get NR. So here the center of mass will lie on each median. It implies that here if we think about the intersection of all these three medians, then it will give you the centroid of the triangular lamina. Means here the center of mass of this particular triangular lamina will lies on the centroid, which one is nothing but the geometrical center of this one. Clear to all of you? Now example 6.3. Find the center of mass of a uniform L-shaped lamina, a thin flat plate with dimensions as shown. The mass of the lamina is 3 kilogram. Now see here, the coordinates for the vertices of the lamina are shown in the figure for the coordinate system here considered as shown in the figure. Now this one is uniform lamina, and here for this L-shaped lamina there are 3 squares in it, and due to its uniformity, here we can say when its mass is 3 kilogram, each square that will be with mass 1 kilogram. Now here, suppose the center of mass of these squares are C1, C2 and C3, right? Which are their geometric centers. So their coordinates, so for C1 the coordinate will be here 0.5 and 0.5 means half. See here. Then after for C2 we can say x coordinate that is 1.5, that is 3/2, and y coordinate is half. Then for C3 the x coordinate that will be 0.5 means 1/2, and y coordinate that will be 1.5, so that is 3/2 respectively. Clear? Now here the x coordinate for the center of mass of this L-shaped lamina, right? That we can give by x equal to m1x1 plus m2x2 plus m3x3 upon m1 plus m2 plus m3. But each square have the same mass, 1 kilogram. So here m1 that is 1, x1 1/2 plus sorry m2 1, x2 3/2 plus m3 1, x3 1/2 upon 1 plus 1 plus 1. And you will get x coordinate that is 5/6 meter. Now similarly y coordinate for the center of mass, that is y equal to m1y1 plus m2y2 plus m3y3 upon m1 plus m2 plus m3. Substituting all the values again when we solve it, we'll get the y coordinate that is also 5/6 meter. So here the center of mass of the L-shaped lamina that is at 5/6 meter. Clear? Now next topic, that is motion of center of mass. See here, we already discussed about the position of the center of mass and the position vector for the center of mass of the body having n particles or system having n particles, that is RCM equal to m1r1 plus m2r2 up to mnrn upon capital M, where capital M that is the total mass of the system. Now take this capital M on left hand side. Therefore M vector RCM that is m1r1 plus m2r2 up to mn rn. Now here m1, m2, m3 up to mn are the masses of the constituent particles, and r1, r2, r3 up to rn vectors are their respective position vectors. Now here by considering the masses of the constituent particles as a constant, let's differentiate this equation with respect to time t. So we can write capital M drc m by dt on left hand side, that is equal to m1 dr1 by dt plus m2 dr2 by dt plus up to mn drn by dt. Now differentiation of the position with respect to time t will give you the velocity. So drc m by dt will give you the velocity of the center of mass. dr1 by dt will give you the velocity of particle number 1. dr2 by dt that is the velocity of particle number 2. Like that drn by dt that is the velocity of particle number n. So we can write the equation mvcm equal to m1 v1 plus m2 v2 up to mn vn. Now take this m on right hand side. So we will get the equation for the velocity of the center of mass of a system. That is VCM equal to m1 v1 plus m2 v2 up to mn vn upon capital M. Now, here VCM, that is the velocity of center of mass, we already discussed, and v1, v2, v3 are the velocities of the individual constituent particles. Okay? Now, from this equation, m VCM equal to m1 v1 plus m2 v2 up to mn vn. Now we can write m1 v1 mass into velocity, that is linear momentum. So m1 v1, that is the linear momentum of particle number 1, so p1. m2 v2, that is p2 up to mn vn, that is pn. Now the summation of the linear momentas of each and every constituent particles here on right hand side, see. So vector sum of the linear momentas of each and every constituent particle will give you the total linear momentum of a system of particles. Let's represent it with P. So we can write m VCM equal to P, that is P1 plus P2 plus P3 up to Pn. Okay. Now see here, this one is the total linear momentum of a system of particles, and P1, P2, P3 up to Pn are the individual linear momentas of the constituent particles. Now see here the result. The total linear momentum of a system of particles, that is equal to the product of mass of the system and velocity of the center of mass of the system. See, actually when we discuss the definition of linear momentum, we say this thing, linear momentum of a particle, that is equal to mass of the particle into velocity of the particle. Here total linear momentum of the system equal to total mass of the system into velocity of the system is not appearing, but VCM, that is the velocity of center of mass of the system. It implies that now here you can understand the importance of center of mass of the system. Now here you can understand the center of mass of the system itself behave as a system. Or in other words, we can say center of mass of the system, that is the representative of the system. Clear to all of you? Now next topic, that is Newton's second law of motion for a system of particles. Now see, we discuss the equation m VCM equal to P1 plus P2 plus P3 up to Pn, that is equal to P. Now differentiate this particular equation with respect to time t. So m dVCM by dt equal to dP1 by dt plus dP2 by dt up to dPn by dt, that is dP by dt. So here we can write now m dVCM by dt, that is dP1 by dt, that is F1, force acting on particle number 1, dP2 by dt, that is F2, force acting on particle number 2, like that dPn by dt, that is Fn. Now vector summation of the forces acting on each and every constituent particle will give you resultant force acting on a system of particles. So that is equal to F. Or here we can write the same equation like this, m ACM, because differentiation of velocity with respect to time t, that give you acceleration also. So m ACM equal to now F1, that is you can write m1 A1 plus m2 A2 up to mn An, that is equal to F. Now here the force F, this one, that is the resultant force acting on a system of particles, and that is nothing but the vector summation of the forces acting on the individual particles here. Clear? And A1, A2, A3 up to AN are the acceleration of the constituent particles. Now, this equation we can summarize like this: m dvc m by dt equal to dp by dt, that is equal to m acm equal to f. Now, see, dp by dt, that is equal to f. But at present we can't say this is Newton's second law of motion for a system of particles. No doubt, dp by dt equal to f, that we say Newton's second law of motion. But here, this resultant force, actually that is the summation of resultant external force and internal force. So F equal to F external plus F internal. But as per Newton's third law of motion, if we think about the forces between a pair of particles, then force on particle 1 by 2 and force on 2 by 1, both these forces are equal in magnitude but opposite in direction. So vector summation will be 0. So in this manner, the resultant internal force between the constituent particles, that will be equal to 0 as per Newton's third law of motion. So here whatever the resultant force or net force appears acting on a system of particles, itself is external force, right? So now we can say this is Newton's second law of motion, because as per Newton's second law of motion, the rate of change of the total linear momentum, that is equal to external force, right? So we can write now the resultant external force acting on a system or system of particles is equal to the rate of change of total linear momentum of the system. So in this way, we derived here the Newton's second law of motion for a system of particles, right? And it is exactly like we discussed for a particle. Clear? So here the center of mass of the system moves under the influence of the resultant external force F. Here we can see F equal to m acm. Again here, this is the resultant external force, that is equal to mass of a system of particles, but acceleration of a center of mass is appearing here. So here the center of mass of the system moves under the influence of the resultant external force F, as the whole mass of the system is concentrated at that point center of mass. It behaves like that, or in other words we can say center of mass behave like system itself, or we can say center of mass, that is the representative of entire system. Now see, here if we take this resultant or net external force acting on the system of particles, that is equal to 0, then we can write dp by dt equal to 0. So P, the total linear momentum of the system, that remains constant. But here this total linear momentum, that is the vector summation of the linear momentums of individual constituent particles. So we can say the vector summation of the linear momentum of individual constituent particles, that remains constant. But here very important thing which you have to keep in your mind, that is this individual linear momentas of the constituent particles may change, but the change will take place in such a way that this vector summation, means the total linear momentum of the system in the absence of resultant external force that remains constant. So we can say this is the law of conservation of linear momentum for a system of particles. Now see, you can understand this thing easily. If resultant external force that is 0, then total linear momentum remains constant. Individual linear momentum of the constituent particle may change, as well as we know if F equal to 0, then F equal to m ACM, m is not 0, so acceleration will be 0. It implies that if the system is in the motion, then it will continue motion with constant velocity of center of mass. And if it is stationary, then center of mass that will remain stationary. See here, in this example we can observe this thing. If a heavy nucleus Ra disintegrate or split into lighter nuclei Rn and He, and if it is in motion, right, then if external force is not acting here, the individual linear momentum of these constituents He and Rn changes. Clear? But these changes will take place in such a way that the total linear momentum that remains constant, and when it is in motion, the center of mass of the system will continue the motion with constant velocity. If we consider this second case, in which if Ra, that is stationary, and it is splitting in two lighter nuclei He and Rn, so again here we can say the linear momentum of He and Rn changes. Initially when these two were the part of system, at that time their linear momenta was 0. Now they have some linear momentum because they are flying in different directions, right? Okay. But here this change in the linear momentum of He and Rn will take place in such a way that the total linear momentum of the system will remain constant. Means before splitting and after splitting, total linear momentum will remain same. And here system is stationary, means acceleration is 0, right? So after splitting also, the center of mass will remain stationary for a system of these He and Rn, two constituent particles. Clear to all of you? Now example 6.4. Find the scalar and vector product of two vectors, vector A equal to 3i caret minus 4j caret plus 5k caret, and vector B that is equal to minus 2i caret plus j caret minus 3k caret. Now see here, first let's take scalar product. So vector A dot vector B, that is 3i caret minus 4j caret plus 5k caret dot minus 2i caret plus j caret minus 3k caret. So here dot product that we know, ax bx plus ay by plus az bz. So ax bx, so that is minus 6, ay by, so minus 4 into 1, that is minus 4, az bz plus 5 into minus 3, that is minus 15. So our answer that is minus 25. Now vector product. Vector A cross vector B, that is vector product, is represented by the determinant I caret, j caret, k caret, ax, ay, az, so 3 minus 4, 5, bx, by, bz, so minus 2, 1, minus 3. Now we have to solve this determinant. So first we take I caret into minus 4 into minus 3 minus 4 into minus 3 minus 5 into 1. Then after minus j caret. So minus j caret. So 3 into minus 3. So 3 into minus 3 minus 5 into minus 2. 5 into minus 2. Then plus k caret. So 3 into 1. 3 into 1 minus 2 into minus 4. So that is equal to, now I caret into minus 4 into minus 3, that is 12, then minus 5, then minus j into minus 9 plus 10, then plus k caret into 3 minus 8. Clear? So finally you will get the result, that is here minus plus 7 I caret, here minus j caret, and here minus 5 k caret. Now in theory we state this thing, A cross B and B cross A will be equal in magnitude but opposite in direction. So suppose you take B cross A, then you can give the answer, that is minus 7I caret plus j caret and plus 5 k caret. Clear to all of you? Now dear students, next topic, that is angular velocity and its relation with linear velocity. So previously we studied about linear motion, or we can say translational motion. So in that we discussed this thing, if you want to explain the motion in detail, then you have to think about some physical quantities associated with that motion. So we discussed about linear velocity, linear acceleration, then force, linear momentum, etc. In the same manner, if we want to explain the rotational motion in detail, then we have to think about some physical quantities associated with rotational motion, like angular displacement, angular velocity, then angular acceleration, then angular momentum, torque, like that. Okay? So first we have to think about angular velocity. Okay? Now we know this thing, in rotational motion, each and every constituent particle of the rigid body execute circular motion, and centers of their circular path lies on an imaginary line, which we say that is the rotational axis, with respect to which the entire body is executing rotational motion, and each and every particle is executing circular motion in the plane which are perpendicular to the rotational axis. As shown in this particular figure, suppose we consider here any point P of this particular rigid body, which one is rotating with respect to this Z axis. So here particle P is executing circular motion, and center of its circular path C that lies on this rotational axis. Here R, that is its radius of a circular path, or in other words we can say that is the perpendicular distance of that point P with respect to this rotational axis. Now, suppose in time interval delta t, particle P reaches at position P dash. And here suppose the angle subtended at the center, this angle PCP dash, that is delta theta. Okay. So this delta theta, that is called angular displacement of the particle. And this one is the rigid body. Relative positions of the constituent particles never changes. Therefore, whatever is the angular displacement of any particle itself is the angular displacement of entire body. Now here we can say this thing, in time interval delta t, the angular displacement, that is delta theta. Okay. So average angular velocity or average angular speed, that we can write omega, that is equal to angular displacement upon time interval. So that is delta theta by delta t, because angular displacement that we discussed, that is delta theta, and that is in time interval delta t. Here angle is measured in radian and time, that is in second. So here unit that you can write radian per second. Now here suppose we take limit delta t tends to 0. Then in that particular case we will get the instantaneous angular speed, and that is omega equal to limit delta t tends to 0 delta theta by delta t, and we can write this one as omega equal to d theta by dt. Right? Here you can see the analogy with linear motion also. Right? The differentiation of a position with respect to time t, dr by dt, that give you linear speed. Here the differentiation of angular displacement with respect to time t, that give you angular speed. Okay. Now here unit that will be radian per second or rotation per second. Clear? And this one is the angular speed of entire body that we already discussed. Now when angular speed is represented with direction, or we can say if a proper direction is associated with angular speed, then it is called angular velocity. Okay. Now here the direction of angular velocity that can be fixed with the help of right hand screw rule. Now how we have to use this particular right hand screw to fix the direction? Okay. So we have to place right hand screw parallel to the rotational axis. Okay. So suppose this one is our rotational axis, and parallel to it, this one is the right handed screw that is placed. Now suppose your body that is rotating like this, then you have to rotate this right handed screw in the direction of the rotation of body. So you have to rotate right handed screw in same direction like this. And if you rotate this right handed screw in this manner, or we can say the direction in the rotation of the rigid body, then the direction in which right handed screw transverse, that is the direction of angular velocity. Here simply you can represent this one with the help of right hand thumb rule also. If this one is your rotational axis and your body that is rotating like this. Okay, so encircle your fingers of right hand in the direction of the rotation. Your body is rotating like this, so you encircle the fingers in the direction of rotation, then thumb automatically will point you the direction of angular velocity. If your body is rotating in this manner, encircle your fingers like this, then your angular velocity is in downward direction, right? And if this one is rotating in this manner, encircle your finger, your angular velocity that is in upward direction. So here, remember one thing, angular velocity that is always along the rotational axis, either in upward direction or in downward direction. But it is always along the rotational axis. Clear to all of you? Now next topic, scalar and vector relation between angular velocity and linear velocity. Now see here, suppose as shown in the figure, a rigid body is rotating with respect to z-axis as shown in the figure, okay, and here in time interval delta t, our reference particle of the body moves on the circular path from P to P dash. So we can say its angular displacement in time interval delta t, that is delta theta. But now here we want a linear speed also, so we have to think about linear displacement. So when it is moved from P to P dash, then it is executing circular motion. So we can say the linear displacement, that is arc PP dash, that is arc PP dash. So here by definition we can say average linear speed, that is linear displacement arc PP dash upon time interval, right? So arc, that is angle into radius. So we can write arc PP dash, that is r delta theta upon delta t. So average linear speed, that is equal to r into delta theta by delta t, that is average angular speed. Or simply we can write by taking instantaneous linear speed, v, that is by taking limit delta t tends to 0, v that is equal to r d theta by dt. So v that is equal to r omega. This one is the scalar relationship between angular velocity and linear velocity. Now here we want the vector relationship. So vector relationship means on right hand side say r, that is the position. So we can take it as a position vector r. Omega, that we can take angular velocity, both are vector quantity. And result we want linear velocity, that is also a vector quantity. So on right hand side there is a product of two vectors, and result on left hand side we want vector quantity. So very simple thing, we have to take vector product on right hand side. Now here, if we think about the vector product on right hand side, then two possibilities are there. You can write vector v equal to vector r cross vector omega, or you can write v equal to vector omega cross vector r. But we know this thing, r cross omega and omega cross r. These two are equal in magnitude but not in direction. Directions are opposite. It implies that both the relationship are not true. So which one is true one? Let's think about v equal to r cross omega. Now we already discussed here in this particular case, your omega that is in upward direction. This is your rotational axis. Your body is rotating like this. So thumb is in upward direction. So now think like this. This one is in upward direction. Itself is your omega. Okay? Now, this one is position vector R. Now we want R cross omega. Okay? So we have to place again here the right hand screw as we discussed for the direction of vector product of two vectors. We have to place this right handed screw perpendicular to both omega and R. Now we want R cross omega. So we have to rotate this right handed screw from R to omega. R to omega. So rotate this one like this. Okay. So now if you want to rotate this one in anti-clockwise direction, then encircle your fingers like this. Then thumb shows this thing. This will transverse in outward direction. So if this one transverse in outward direction, so if you place this vector here, then velocity that will be in tangential direction outward. But see, in our case, velocity that is inside here, see tangential. It implies that if you take R cross omega, you are getting outward direction. Now you can easily understand. If you take omega cross R like this, then if you rotate right-handed screw in this manner, thumb pointing inward. So that particular relation represent the correct direction. Means this relation is not valid one, but this one is the correct relation. So we can say now scalar relation between linear speed and angular speed, that is V equal to R omega, and vector relation between linear velocity and angular velocity, that is vector V, that is equal to vector omega cross vector R, right? Because we discussed this thing, this one is not representing the proper direction. So correct relation, that is omega cross R. Clear to all of you? Now next topic, that is angular acceleration. Now see here, suppose instantaneous angular velocity is at time t and t plus delta t are omega and omega plus delta omega. So here we can say this thing, the change in angular velocity in time interval delta t, that is delta omega. So as per definition we can say average angular acceleration, that is change in angular velocity upon time interval. So we can write average angular acceleration, which is represented by alpha, that is delta omega by delta t. Now again if we take here limit delta t tends to 0, then we will get the instantaneous angular acceleration. So angular acceleration, that is limit delta t tends to 0, delta omega by delta t, or we can write vector alpha, that is d omega by dt. Now here the direction of alpha, now be careful here, very important thing. It is not necessary alpha is always in the direction of omega. You have to remember this thing. It is in the direction of change in angular velocity. Change in angular velocity. Okay? No doubt that will be also along the rotational axis. But it is in the direction of change of angular velocity. I represent that thing. See, now here if you write the unit, then radian per second square or rotation per second square. Now see here, Suppose at time t, this one is omega, right? Direction, and as per its magnitude, we take the length of the vector. But now suppose, see, body is rotating like this. See my finger. And then after some time, it rotates like this. Now you can understand, magnitude of velocity increases but the direction is same one. So you can represent